So here we go. We're starting with lesson 1, fundamental identities. We're going to talk about what's a reciprocal, quotient, and Pythagorean identity, and we're going to look at proofs and some expression manipulation. First definition of an identity. An identity is an equation that is satisfied for all the values of the unknown. Or the variable, whatever it's easier to write the value of the variable. For which both sides of the equation are defined. The first type that we call reciprocal identities, we already have seen cosecant, secant, and cotangent. They are called reciprocal identities because we can obtain them by doing one over another trigonometric function. So cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tan. Now, for each of these ones, if we consider them to be identities, so truths for both sides of the equality for all of the values of the unknown, for which the equation are defined on both sides, we define them by talking about the NPVs, right? So what's going to be the NPV for the cosecant? Cosecant is obtained by doing 1 over sine. So what we don't want is have this expression equal to 0. So we want to exclude all possible angles where sine of that angle equals 0. What are those angles? Oh, that's not for sine. Cosine is at 90, right? That's right, 0, 180, or 0 and pi and so forth. So 0, pi, 2 pi, 3 pi, 4 pi, and so forth, that's multiples of pi because you count them, every single one of them, right? So we simplify that expression by saying it's a multiple of pi. So pi k is our NPV for cosecant, and for all of them we have to say what k is. K is an integer. Now for secant, we don't want cosine to be 0 because cosine is at the bottom of the expression, 1 over 0, we want to exclude. So where is cosine being 0? Now it's going to be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. And we notice how we count only the odd multiples of pi over 2. So for that, we write it like this, 2k plus 1 as a multiplier for pi over 2, and that 2k plus 1, it just counts only the odd numbers. Cotangent, for that we need to figure out where tangent of theta equals 0. Do we remember where tangent of theta equals 0? Or it can be at pi over 2 odd multiples because that's where the NPVs for tangent are. It's not 0, is undefined, right? Yeah. So it's the other one, which is 0 and 2 pi and again 3 pi and so forth. It's going to end up to be 0 because that's those points is 1. It's 1 0, and then you have 0 divided by 1, which is 0, right? For the values of tangent. So k belongs to z for this one as well. It means the numbers that we talk about here for k, they're integers. So you say k is 0, k is -3, k is +5. That's right, yeah. Z is the name of the integer set of numbers, yeah.
Cosine and tangent have the same, basically have the same NPV there.
Secant and cotangent have the same NPV, that's right, because they end up with the same location for their points, you know, where both cosine and tangent are 0, right? But not these ones, cosecant and cotangent, that's what we're talking about, right? So cosecant and cotangent have the same NPVs, yeah. These are the only two types of NPVs you can have, by the way, right? Either you have NPVs that you have to exclude at pi multiples, or NPVs you have to exclude at pi/2 odd multiples. There's no other ones, okay? Okay, quotient identities are identities that are obtained by dividing two known functions, okay? The only two ones that we have are tangent and cotangent. So a tangent is sine over cos. Remember our formula y over x, right? Y is sine on the unit circle, x is cosine on the unit circle. So there it is as a quotient identity. And then cotangent will be just the reciprocal of tan, so you just flip over the same fraction, so it's going to be cosine over sine. Now, what are their NPVs, right? Again, we're going to look at their denominator. Whatever makes those ones 0, that's what the NPVs are. The tangent one, we already know because we discussed it quite a bit, right? So it's going to be odd multiples of pi/2. And for cotangents, we already discussed it over here. We already know it's pi k, but now you can see it's probably a little bit easier when you see it as a quotient identities because you have sine of theta equals 0. So it's easier to identify that where is sine equal to 0? Oh, it's at 0 and pi and 2 pi and 3 pi and so forth. So pi k belongs to z. So these identities are only true for all of these angles except for their NPVs. Okay, so not true for their NPVs because they don't exist, right? Either the left-hand side or the right-hand side doesn't matter, they are not true. Pythagorean identities, our last one. We start with a very basic Pythagorean identity that stems from the equation of the unit circle. On the unit circle, we said that inside the unit circle, all of those central angles and those triangles that are forming inside the unit circle are those right angle triangles with an X and a Y for the arms of the right angle, and the R being your higher hypotenuse of the right angle triangle. So in that right angle triangle, you can put x squared plus y squared equals y squared, and it creates the equation of a circle around the origin. If the R is 1, that became our unit circle, right? So that's where this equation comes from the equation of the unit circle. Cosine is our x coordinate, you just square it, and sine was our y coordinate, you square it, you add it together, and you get your R squared, right? So cosine squared theta plus sine squared theta equals 1. That's what we call the Pythagorean identity. And this one is true for all values of your theta because cosine and sine have no NPVs, right? So it's always true. Now for this original Pythagorean identities, which by the way is in your formula sheet, so you don't need to memorize this one, we can derive other ones. So if in an expression, and we're gonna do proofs in this unit, I need to convert the cosine squared theta into sine squared theta expression. I can use this identity if I manipulate it. If I move everything on the left-hand side or some selected values on the left-hand side or the right-hand side, I'll get what I need. So if I isolate the sine squared theta, so I focus on leaving sine squared theta on the left, right here, and then that means I have to move cosine squared theta on the other side, right? I'm gonna get a new Pythagorean identity, if you like. that has sine square on the left and 1 minus cosine square theta on the right. So if I want to write something like a sine square expression into cosine expression, I would have to use this equality. Same thing for cosine. If I want to isolate cosine by itself, that means I have to move sine on the other side. I'm going to get a second type of Pythagorean identity. And these are pretty easy to remember. The other two are going to be obtained by dividing each of the terms of the Pythagorean identity by one of them. So if you choose to divide it by sine squared theta, you're going to end up with cosine over sine, sine over sine, 1 over sine, okay? And those ones all mean something else, either if you look from the perspective of a quotient identity or from the perspective of a reciprocal identity. So cos over sine is cotangent. You just have to square it because both of them are squared, okay? So cotangent squared. Sine over sine is 1, right? 1. And 1 over sine, that's cosecant. Again, we have to square it because it's a squared value, a squared expression. So we get our third level of Pythagorean new identities. And if we divide all of them by cosine, we're going to end up with 1 here. Sine over cos is tangent. We're going to square it. So tangent squared theta. 1 over cos is secant. So secant squared theta. Now, this is in the formula sheet. Find your formula sheet. I want you to find it on your formula sheet. That first Pythagorean identity. Found it? Okay. How about these two, the next two? 1 minus cos squared theta, 1 minus sine squared theta. No? No. So you got to memorize those ones or recognize them. This is not a new thing piece. This has been, yeah, that's the formula sheet, right? Yeah. And then the last two. Can you find the last two? Yeah. So these two are, so these are not in there. These are in your formula sheet. So make sure you know how to find them, and then obviously later on how to use them. There should be some extra ones on that purple tower because this is the formula sheet for the course. It's not specific for this unit. Okay, so let's start with a little bit of work, algebraic work on simplifying trigonometric expression. This is prep work towards proving identity. So why do we do this one? Because identities allows us to use given trigonometric expression in a much simpler form. And when we're going to simplify, we're going to use some arithmetic techniques, for example, adding, subtracting, multiplying, dividing fractions, algebraic techniques like factoring, special polynomial products, like terms, and so more than that, of course, because algebra is huge. And then we're going to combine all of these with the given fundamental identities that we had learned so far. Make sure you do practice a lot because they are a skill, and since it's a skill, it has to be practiced, right? So you have to be, yeah, you have to have some hours in until you can be confident that you know what you're doing with these ones. Simplify the following trigonometric expressions. I already have a lot of keys for this unit because it tends to be a little bit more difficult, but I always do the work anyway on paper because I don't like to teach on solutions. So we have sine of x plus cotangent x times cosine of x, and we are asked to simplify it. Well, what does it mean to simplify? Well, to simplify means what? Let's see what it means to use this.
Mhm.
You do? Okay. Okay. In what way reduce?
Expression,
Hmm?
make the expression simple.
Simpler, that's right. You have to make it simple looking, right? That it is, okay? So if at the end of your simplifying, you get to with an expression that looks more complicated than you started with, what's the point of that? There's no point, right? So you want to make it look simpler. So if you have an addition, a subtraction, maybe you can put the terms together in some way that is going to make it simpler. If you have multiplication, division, maybe if you process that, also will make it simpler. Maybe some cancellations will happen. Okay, so or sometimes we have to use identities to exchange some of the given functions into another one. So maybe that's going to make it simpler looking, right? Now, normally the rule of thumb is that we always use for identities. If I have something that's not a cosine or a sine, okay, like cotangent, tangent, cosecant, secant, change it using identities in terms of sine or cosine. So the one that doesn't have, right, it's not a sine or cosine, is cotangent of x. So I'm going to keep everything around it the same way. When I get to cotangent of x, I'm going to use the quotient identity. So I'm going to use cosine of x over sine of x times cos of x. So far, so good? Now again, I'm gonna have to use what I can, because once I replace cosine x and sine of x for cotangent, now I have a multiplication that I can process, right? I can do cos times cos for the numerators and sine times 1 for the denominator. You can always put a 1 there so you can see it. Sine of x so far stays by itself. I'm only gonna work here. So cos x times cos x is cos square x over sine of x. Now, it looks like we're going in the right direction. Because I have done a lot of these things, I can already see like 2 or 3 steps ahead. It's kind of like playing chess. Anybody plays chess here, or at least knows the rules? Like you can't play chess unless that you develop a way for your brain to see ahead of the moves. So you're making a plan in your head, like if I do this move, then he'll do that move, and I'll do that one, and then you can see that the more steps you can see ahead of yourself, the better chances you are, right, to win at that competition. I'm very bad at chess, by the way. I cannot see ahead. I don't have the patience for it, but that's how it works. You have to know strategies, right? Same thing here. Like I already know that once I replace here, things will start to work for me and I can see where they're gonna go. You might not see it, but you will if you do a lot of practice questions. Now, what I have to do here is put these two fractions together. They might not look like fractions to you, but if you put here over 1, it becomes a fraction. And then in order to add two fractions, we have to bring them to the same denominator. What's the common denominator between 1 and sine of x? Sine of x. I didn't have sine of x here at the bottom, so I have to multiply with sine of x, top and bottom, right? That's going to make it sine squared x. Here I did have sine of x, so nothing gets to be multiplied or amplified, we call it. And as soon as you get sine squared theta plus cos squared theta, that's going to be equal to 1. That's your Pythagorean identity. So we're going to replace the expression sine squared theta plus cos squared theta, or vice versa. When you get it backwards, that's fine as well, right? Cos squared theta plus sine squared theta, still the same thing. That's equal to 1. A lot of the times, this saves us quite a bit. Okay, so when you get to a Pythagorean identity, look how nice it simplifies to all of that to 1, right? 1 over sine of x. And then we can take it one more step. Instead of writing as a reciprocal, I can write the name of this reciprocal. What's the function that's the reciprocal of sine? cosecant of x. And that's it. Okay, so that's how you simplify it. Do one more. So we have sine theta plus cos theta plus cos theta over 1 plus sine theta. The rule of thumb is usually if you have anything that's not in terms of sine and cosine, to exchange it into that. When you have no idea, usually you go there, okay? Now, these are all sines and cosines, right? There's nothing to do in terms of the rule of thumb. So I'm stuck here is, okay, try to put these two fractions together by adding them up, right? So I mean, I will have to find a common denominator between cosine of theta and 1 plus sine of theta. They're all different, both of them. So that means their common denominator is just the multiplication between them two. So cosine of theta times 1 plus sine of theta, that's the common denominator. Now you gotta be careful once you get your common denominator to see what you have to multiply the numerators of the previous fractions to create those equivalent fractions. So what do we have to multiply sine by?
Cosine plus 1.
1 plus sine of theta. Right, so the other one, 1 plus sine of theta. And the other one, cosine. All good? And then we just write sine of theta, 1 plus sine of theta, plus cos of theta squared, so cos squared theta. Okay, so we got to the step, we got the multiplication at the top. We already multiply here, because usually when you can, like, you can simplify your steps in your head, so you don't have to go and show every single step of the way, as long as it's clear of what you're doing. So we're gonna move on and simplify more at the top. But I'm gonna leave the bottom as a multiplication, because again, I already know what I'm gonna be getting. You know, I know what's gonna be canceling, so I want to keep this uncanceled. Like if you are opening up the bracket, you'll notice right away that you have to go back to the original form, because then you're stuck, you don't have anything else to do. So here we open, so we do distribution. We have sine of theta plus sine squared theta plus cos squared theta. And then we notice that we have the Pythagorean identity, which equals to 1. So we have sine of theta plus 1, cos of theta 1 plus sine of theta. Now 1 plus sine of theta or sine of theta plus 1 is the same thing, right? Addition is commutative. So the whole bracket cancels with the whole bracket over there. And we get 1 over cos of theta, which is secant of theta. Simplified. Okay, one more, I think, before, yeah. Cos cubed of x plus sine squared of x times cos of x. Now, Here, again, everything is in terms of sine and cos, so that rule of thumb is gone. I can't really add fractions or combine them because they are not combinable, right? So the only option is now to kind of go backwards and factor some things out if it's possible. Now you have cos cube here, and in the next group, the next term, right, you have also a factor of cosine, right? So basically, you can rewrite that as cos of x times cos square x plus sine square x times cos x. And that way you can see the factors individually, right? Is that clear? Okay, so cos times cos is cos cubed, right? All I've done is just open it up so you can see the common factor. So cos of x, common factor, we write it once, open the bracket. And inside the bracket, we have what's left over in each of those terms. So we have cos square x plus sine square x, which is ding, 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 Pythagorean identity, which equals to 1. So we end up with cos of x times 1, which is just cos of x. Now, I did give you a your turn booklet with solutions. Can you check the 1.1 if it's the right one? Because I remember changing it and I'm not sure if I copied the new one or the old one. Can you see if your questions match? Because if they don't, I'll just photocopy another one. Is it good? They match these ones? Greg said yes. Yeah. Okay, good, good. Just want to make sure. Proving identities. Proving identities is going to be based on the scale of simplifying expressions, but you have to show that an equality is the same expression on each side of that equal. It usually starts with a more complicated looking equality, and you have to boil it down to something simpler looking so that you can show that the left-hand side will equal the right-hand side. Okay, now we're going to start example number 2, the simple one, because the expression is only on the left-hand side, and on the right-hand side, it's just a number equals to 1. So whatever we do here on the left, it has to simplify to number 1. We don't replace data with anything. We just have to use identities to replace the given trigonometric functions with other ones in such way that they will cancel out. Okay. So you have some recommendation. Among these recommendations, you will see the one change everything in terms of sine and cosine. Add when you have fractions. Sometimes you have to separate a given fractional form into 2 separate fractions. It's really anything you can think of in terms of algebraic or arithmetic methods that it's gonna make you prove the identity. It's not, these are all like sort of things that we use in other mathematical situations that just work for the identities. The only one that's kind of a little bit different is number 6. And we're only using number 6 in specific cases, and I'll show you the specific case when really anything else doesn't work. Okay, number 6 actually introduces something extra in the identity, just like the rationalization would do, introduces that square root into it to simplify it. The same thing we're going to do for this conjugate binomial number 6 recommendation. So let's start with the example 2 here and just prove as many identities as we can until the end of the class. So we have sine of theta, secant of theta, cotangent of theta. That's on the left-hand side. And I like to do it like this, left-hand side on the left of a vertical line like this, and then the right-hand side on the other side of the vertical line. And the way I like to do it, or the reason why I like to do it like this, because when you're proving identities, you don't cross over anymore, okay? You cannot add on each side, subtract, divide on each side. You're not doing that. You're working on each side independently of the other side. You basically ignore it a little bit on the other side because you don't have to include it in this side's calculation or manipulation. So let's focus on the left-hand side, and usually we always start with a more complicated side of the equality, and this one is obviously more complicated. And then we see we have secant and cotangent, and I would change everything in terms of sine and cosine. In between these, remember, it's just times. So we have sine of theta, secant is 1 over cos of theta. And don't be lazy, write your thetas. I know that it's just sine and 1 over cos all the way throughout, but yeah, it's important to keep writing your thetas. And cotangent is cosine of theta over sine of theta. And then we simplify. Sine is over 1. And then we can cancel this sign with that sign, right? One is at the top, one is at the bottom. And then we have a cosine at the bottom and a cosine at the top. So we're left with 1 over 1, which is 1. And at the end, we write left-hand side equals right-hand side. And you proved. Jenna, do you remember that fancy end of this? That's right. Or in geometry, usually this is used quite extensively. QED is Latin for saying this has been demonstrated, and sort of a signal that your proof is ending. It's done. So nothing that's written after QED means anything to the proof that you've done, right? So it's kind of like when we do like squaring of the final answer, that's your final or the end line of your proof. And I am trying to memorize the actual Latin words, and every time I say that to my class, it's wrong. And I check after the class, like, oh, I messed up that word again. It's something like quat extra demonstratum. So it sounds like a, a Harry Potter spell. It's in Latin. Okay. So cosine of theta plus tangent of theta times sine of theta equals secant of theta. So this time we have two sides, not just one side and then the other one a number. So I always leave less room for the one that I don't really think I'm going to work much on it. So I'm going to leave less room for secant because I'm going to work on the left-hand side because it looks more complex. So I can simplify that probably a little bit better. So secant of theta stays on the left there. And then I have cos of theta plus tangent of theta times sine of theta on, stays on the right, and on the left. The tangent we write in terms of sine and cosine. And then we put them together. Sine times sine is sine squared theta over cos theta. I think we've done something similar, right, in our simplifying of expressions. So common denominator is cos of theta. That means I have to amplify there with a cosine of theta. Cos times cos is cos squared theta plus sine squared theta. That's Pythagorean identity, which is 1 over cos of theta, which is secant of theta. And we notice that left-hand side, it's equal the right-hand side. Okay, so just so it's clear for everybody, because you know our class is quite small, but when I have bigger classes, there's always one or two students asking me, what's LHS? Okay, what's RHS? It's left-hand side, right-hand side. Okay, so just so I'm clear, and I say it specifically.
D at the end or just?
No, just a D.
Just a D?
D. Yes. I took Latin, I think, a couple of years in high school, grade 9 and grade 10, I think. We did take Latin. And there's so, you know how when you learn French, you have to learn all of the ends of like your conjugation of your words, like the same thing for Latin. Oh man, we used to write it on our hands, you know, and it was, for the test, there were so many, we couldn't remember them all. It was terrible. Yeah, so much Latin. I mean, it does help because you sort of know it a little bit, but you don't remember almost anything. Yeah.
No, I don't.
No. Oh well. That just stems from like an older way of education, right? So okay, but this one I need a new page because I don't have room. So we have negative tangent of theta equals 1 minus tangent of theta over 1 minus cotangent of theta. There's no ta there, it just keeps showing up. I think it's behind this one when I write it with the mathematical expression, and I just can't see it. It only shows up when you print it. Annoying. Okay, so left-hand side is minus tangent of theta. The right-hand side is 1 minus tangent of theta over 1 minus cotangent of theta. And I think, yeah, I've done it with cotangent as well. So you can do this one too. If you want, you can change everything into sine and cosine. But if you notice that you have tangent and you have the reciprocal of tangent, there's no point of going there. So you're hoping that if you change cotangent into tangent, then hopefully something will happen and you can simplify it down to this expression, right? So that's what I would do. I wouldn't go to sine and cosine unless I really would have to. There's 3 different kinds of trig functions. So let's start with that, changing the cotangent of theta into 1 over tangent. And then we're going to focus on the denominator of this bigger fraction and then combine these two. Okay, this is 1 over 1. And that means I have to find a common denominator, which is tangent of theta. And then I have to multiply here by tangent of theta. So what's going to be in the numerator? Tangent of theta minus 1. And then here at the top, I haven't done anything to change it, so I just copied it. So here's your fraction line, here's your fractional line. Okay? You can see it. Comparison. Okay, so now this fraction line just means divide, right? That means I have to divide the 1 minus tangent of theta by this fraction. How do we divide fractions? That's right. So we keep the first one exactly how it is, the 1 minus tangent of theta. It's not really a fraction, so it's just going to be over 1, right? So we keep that exactly the same it is, this one over here. And then we times it by the reciprocal, the one at the bottom. So tangent of theta over tangent of theta minus 1. Now, I'm noticing I have 1 minus tan at the top, and I have tan minus 1 at the bottom. Oh man, they're so close, okay? Which is vice versa of one another, right, in a subtraction. What can I do? Well, I can make one look like the other one by factoring out a -1. Okay, that just switches the order of the terms. So let's do it for this first term here. -1 bracket. That just makes the negative tangent positive tangent. So I'm just going to put it in the first position so it's nicer. And makes the positive one a -1. Okay, we copy the second fraction. And now we have something to simplify, right? We have tangent -1, tangent -1. But what are we left with is important. It's not just tangent. You have to remember you have a -1, right? So -1 times tangent is just negative tangent of theta. And then we have the left-hand side finally equaling the right-hand side. So we are done. Okay, so this is question D, I think, yeah, D. We have tangent squared theta over secant of theta plus 1 on the left-hand side and 1 minus cos of theta over cos of theta on the right-hand side. Now, which one is more complicated looking? Well, I would always choose the ones that have like squares in them, that have different functions that are different in sine and cosine. There's not much you can do on the right-hand side here. You can just split this up into 2 separate fractions and then what, right? So I would definitely choose to work on the left-hand side. And since my right-hand side is cos, I would change everything in sine and cos. So let's do that. Tangent is sine over cos. Just make sure you square it because your tangent is squared as well. So sine squared theta, cos squared theta over secant is 1 over cos plus 1. Now I can't go to divide by the reciprocal because at the bottom I don't have just a nice combined fraction. So I would have to combine the fractions first. Common denominator is, for these two, cos. At the top, I'm just going to copy the sine squared theta over cos squared theta, and then common denominator cos of theta. Nothing changes in the first fraction, but here you have to multiply by cos. So 1 plus cos of theta. Now this main fraction line it means divide. So we have sine squared theta over cos squared theta times by the reciprocal of it, cos of theta over 1 plus cos theta. And the cos from here with one of the coses from there cancels out, right? Remember, cos squared theta means cos times cos, right? So one of them cancels out and we're good. Now I would want, like, because you always kind of look over on the other side. You don't include the other side in your calculations, but you look over and see, are you close to what you should be getting, right? And I'm looking on the other side, I should have a cosine by itself into the denominator. And after this cancellation, I will have a cosine here by itself. The problem is this, 1 plus cosine of theta. I shouldn't have that in here at all. And I actually should have a similar one at the top with 1 minus cosine, right? How can I get there? Well, sine squared theta, I can write it using the Pythagorean identities, one of the other ones we derived from the main one in terms of cosine. Okay, and that's going to create a difference of squares. Every time you have 1 minus a squared of something, that's a difference of squares because 1 is a squared number. Okay, so that's what we're going to do in the next step. So we're going to write sine squared theta as 1 minus cos squared theta over cos times 1 over 1 plus cos of theta. And this is what we call a difference of squares. It's the formula a squared minus b squared equals a minus b, a plus b. That's the difference of square factorization. Equals.
Well, that's more actually, like, the sine squared,
Yeah. The sine squared theta
yeah,
equals that. So we replaced it with that. That's the one of the Pythagorean identities that we created at the beginning of class. Okay. It's just a rearrangement of the sine squared theta plus cos squared theta equals 1. Okay, just a rearrangement of that. And then when you have 1 minus cos squared theta, that's a difference of square. Right? 1 squared minus cos squared. Because 1 squared is still 1. Okay. So far, so good? Yeah? Follow me? I went a little bit off rogue, so I'm doing a little bit different approach. And this, I think it was a little bit different in the notes. Okay. So we're going to open this one up into its factorization. So we have 1 minus cos of theta, like the formula, and then 1 plus cos of theta. Open it up over cos of theta times 1 over 1 plus cos of theta. So Pythagorean identities to do the difference of squares and then open up difference of squares into the factorization. Now, what do you think happens next?
that's what, 1 plus cosine.
Yeah, 1 plus cosine of theta goes away, and that's the whole goal, right? And I knew it's going to come up, and I'm going to be left with 1 minus cosine of theta over cosine of theta, which is the same thing as the right-hand side. Okay, so this is this approach that I came up with this right now as I was doing your notes here. And this is the approach that I've used for your notes when I type this up. I've used the tangent squared theta formula. It's in your formula sheet. It's again one of those Pythagorean identities that we created from the original one. Okay. So we replaced tangent squared theta with secant squared theta minus 1. And this became our difference of squares. Okay, secant squared theta minus 1 can be squared. That's a difference of squares. And that's opening up into the factorized form. And that simplifies into secant of theta minus 1. And then you have to replace secant with 1 over cos, and then you have to do the math for the fractions, right? So a different approach, but again, it doesn't matter the way you approach it as long as you can prove it, right? You have to use a series of methods until you get to the left-hand side equals the right-hand side. This is why these questions are difficult, these proofs, because it's not the cookie cutter for everything, right? It's not the same way. You have to do it your own way as long as you know algebra. And when you have troubles with basic algebra, this is a whole mess, right? It's hard. It makes sense. And here at the bottom, even another solution, probably the one that I've used with you guys, right? Maybe, yeah, I think so. This one, the B. Okay, so E. Sine of theta over 1 minus cos of theta on the left-hand side, and then 1 plus cos of theta over sine of theta on the right-hand side. Everything is in terms of sine and cos. So that rule of thumb out of the window, I can't do it, right? I don't really have separate fractions to, put together, that's already gone too. Not one of them is done more complicated than the other to kind of guide me which way I should start to work. So I'm sort of stuck. So these are the examples where sometimes you have to introduce something extra into your proof to be able to prove it. And the something extra we are talking about is introducing to the binomial you have, because these ones usually have a binomial. Here, have a binomial here, 1 minus cos. It's called a binomial because it has two terms. 1 plus cos is a binomial because it has two terms, right? So for your binomials, if you introduce what we call the conjugate binomial that makes up the difference of squares formula, that's going to lead me to the Pythagorean identity. Okay, so a conjugated binomial is this formula: a squared plus b squared equals a plus b times a minus b. So if we are, let's say we're going to work, because in your notes, I worked on the left-hand side. So I chose to work on the left-hand side. I'm going to show you today on the right-hand side, okay? Just so you can see, it doesn't really matter where you start, okay? So if I'm choose to work on the right-hand side, the binomial that I'm working with is 1 plus cos of theta. That would be your a plus b, okay? Its conjugate binomial is the other one. So if I have to introduce something extra to actually make this entire equality, because I don't have the entire group of two factors, I would have to introduce the 1 minus cos of theta over there at the top of the fraction, right, at the numerator. But again, just like with rationalizing, you're not allowed to just introduce at the top only. You're only allowed to times by 1 something, because that's the only thing that doesn't change the value of the given expression, right? Times 1. So what should I put at the bottom here? Same thing, right? So I have to double it up. This is what guides me at the top, because it's going to give me what's the conjugate one. And at the bottom, I just write the same thing to make it 1, right? Now I have a starting point. Now I have the multiplication to do. So I'm going to do the multiplication. At the top, because I have the conjugate binomial together with its partner, I can just rewrite the expression, but this time as, I put plus there, as a difference of squares, right? So a minus b. So I'm going to write 1 squared minus cos squared theta. That's the difference of squares, but this time with our given expression. And at the bottom, we have sine of theta times 1 minus cos of theta. Now I'm looking over, again, my shoulder, my vertical line, and see what should I have? What am I working towards that I should have and keep? And then what I shouldn't have. So I can see that I've already gotten my 1 minus cos of theta at the bottom, which I should have, right? And I have to get rid of the sine of theta, and I have to somehow come up with the sine of theta at the top, okay? Now, to come up with the next step, you have to recognize this as being the Pythagorean identity, one of the converted ones. Which one is it? What is it going to equal to? Yeah, 1 minus cos squared theta, it was going to equal to what? Because I want to replace it with something else. No, not that one. I don't want to open it up back to what it was. I don't want to open it up to the difference of squares because I already went there. So this was the difference of square factorization, and I went to the difference of squares. So what does 1 minus cos squared theta equal to? Sine squared theta. So I'm going to replace it with sine squared theta. So far, so good. So this replaced that. And then sine theta at the bottom, 1 minus cos theta at the bottom as well. And we can cancel, right? The sine with sine, because now it's all factors. The sine at the bottom goes entirely, and only one of the ones from the sine squared theta goes. So what we're left is with sine of theta over 1 minus cos of theta. Left-hand side equals right-hand side. Done. Then you have some your turn proofs to do there. Make sure you go over them once you're done with studying for your test. So I don't really expect you to study for the next week. So don't worry, okay, about homework and all that. There's gonna be no partial for this unit until Wednesday. That's the first day we will have partial. So proving identities for a given angle. So some questions are gonna be like this, and this is where you're gonna need a unit circle the first time in this unit. All you have to do is work with the values of each of the given functions using your unit circle and make sure that once you manipulate those values into the arithmetic that's given to you, you're gonna end up with the same value on each side of the equal, okay? So we have proved the identity for theta equals pi over 4. So I would start somewhere on my page with pi over 4 angle, unit circle value for pi over 4, right? So we have square root of 2 over 2, square root of 2 over 2, and for tangent I have 1. I would do my unit circle just in the first quadrant, so I have some basic values there to work with. On your left-hand side and your right-hand side, remember, they're not proofs, and then at the end, you just plug in into your final expressions of your proofs. You are expected to work with the values of each of your trig functions. So you start by plugging in the angle in each of the functions. So you have to work with cosine of pi over 4 divided by secant of pi over 4 sine of pi over 4, and these values will have to equal with cosecant value at pi over 4 minus sine value at pi over 4. Okay, so let's start on the left. Each of them have to be evaluated. The first one, cosine of pi over 4. We already have our unit circle values in front of us, so we can just plug in. What's cosine of pi over 4? Square root of 2 over 2. What's secant of pi over 4? Secant is the reciprocal of cosine. So you just have to do the reciprocal of those. So 2 over square root of 2, which, yes, simplifies to something way simpler, but you can just use the values as they are. Times, what's the sine of pi over 4? Square root of 2 over 2. And once you have all of the values, you work with these to simplify, okay? Because a lot of the times these questions are like 5 marks. And then the students just boil it down to one thing and just replace into one thing. And then this is it. That's not it, because you have to show the value for each of them individually, okay? So then we have a square root of 2 over here, cancels with that over there. The 2 from here cancels with 2 from there. So all you have here at the bottom is 1. So we have square root of 2 over 2. That's the value we get from the left-hand side. Now we have to get the same value if we want to prove it on the other side, doing the same method. First, we know what is the value of cosecant of pi over 4, the reciprocal of sine, right? So 2 over square root of 2 minus sine value, square root of 2 over 2. Same denominator, 2 square root of 2, amplified by 2, amplified by square root of 2. So we get 4 minus 2, which is 2 over square root of 2. 2 and 2 cancels out. 1 over square root of 2, which is the same as this one, but we're going to show it by rationalizing. So times square root of 2 over square root of 2. So we get square root of 2 over 2, right? So left-hand side equals right-hand side. Do one more. Prove the following identity for theta equals 5 pi over 6. So only on the left-hand side, I would have to work. And I'm going to give myself a lot of space there. Because what I have to do is cotangent of 5 pi over 6, secant of 5 pi over 6, and cosecant of 5 pi over 6. So I have to work with an angle in quadrant 2 that's in the same family with what theta are. Pi over 6. So pi over 6 is this angle right here, the first one, the 30 degrees, and in quadrant 2, that's the one. What are the points on the unit circle for pi over 6 angle? The cosine square root of 3 over 2, sine is 1/2, and tangent square root of 3 over 3, right? Okay, now I just have to be careful that in quadrant 2, you'll have the x is negative, so negative square root of 3 over 2, the y is still positive, right? And then the tangent value will be negative or positive? Negative, right? So you have to be careful because you're in quadrant 2. For unit 3, you don't have to always, for this kind of question, show theta r and go, to more into detail, as long as you can show this diagram. So show the diagram for first quadrant, and then use that first quadrant to move in the quadrant you're supposed to go. Right? That's still using the reference angles, right? by going to the memorization of the first quadrant. So let's see if we can get this done. Cotangent of 5 pi over 6. So cotangent would be the reciprocal of that. So just flip that upside down. Don't go to 1 over unless you really need to, because you don't remember how to do it, right? 1 over this fraction just flips the fraction upside down, okay? So it's still negative, because we're in quadrant 2, 3 over square root of 3. Secant. Secant is the reciprocal of cosine, right? Cosine is this one. So reciprocal of negative square root of 3 over 2. So 2 over square root of 3 with a negative. Divide by. Cosecant, the reciprocal of sine. So 2. Negative times a negative is a positive, right? 3 times 2 is 6. Square root of 3 times square root of 3 is 3. So at the top, we have 6 divided by 3, which is 2, and then divide by 2, which is 1. Left-hand side equals right-hand side. We have demonstrated. That's it.